Good morning, friends. So, I am Dr. Ravi M. Medalli, Professor and Head of the Department of Electronics and Communication Engineering, SG Balekundri Institute of Technology, Belagavi. We have seen in the last class a discussion about a regulated power supply. The regulated power supply, we make use of this particular supply, right, for even for the laptop charger, maybe even for the mobile charger, and so on and so forth. And even all the semiconductor devices requires a DC power supply. However, the available power is AC, so we need to convert this AC signal into a DC signal and using a regulated power supply. Here in this particular block diagram, okay, we have a transformer. It is called as a step up transformer. That is, the input to this step up transformer is single phase 230 volts 50 hertz AC supply, and this transformer steps down the input of 230 volts to the lesser voltage at the output, and output of the transformer is fed to the rectifier. The main function of the rectifier is to convert AC signal into a DC signal. So, the output of this rectifier will be a pulsating DC, but in fact we want a continuous DC. However, the output of the rectifier, what we are getting is pulsating DC. So, in order to remove the AC ripples from this pulsating DC output, we are using a filter here. So, it could be a inductive filter or capacitive filter. Using a suitable filter, we are able to remove the AC ripple content of the output of the pulsating DC. So, finally, what we get at the output of the filter is a almost a continuous DC signal with a lesser ripples here. So, that output of the filter, it is once again fed to a voltage regulator. As I told you, that voltage regulator, right, usually a Zener diode, it is being used as a voltage regulator. The main job of voltage regulator is, that is two. One is the line regulation, another is the load regulation. In case of line regulation, right, if there is any variation in the input supply, this regulator will provide a continuous output here. Suppose if there is any variation in the output current, the regulator provide the continuous DC output, right. So, therefore, the job of the voltage regulator is to provide a continuous DC in spite of variation in the input voltage or the load current here. So, finally, at the output of this regulator, we get a regulated DC output. And also we have seen in the last class about a single phase half wave rectifier, that is, it is also called as single phase half wave uncontrolled rectifier, because it makes use of a diode here. So, therefore, this half wave rectifier, it consists of, right, it converts AC signal into a DC signal, and this rectifier consists of a step down transformer and a diode and a load here. So, friends, you can see that. So, during positive cycle of this, okay, during positive cycle of the input voltage, so this potential, this terminal will be at positive, right. So, this will be at positive, whereas this terminal will be at negative potential. So, therefore, correspondingly an voltage is induced at the secondary voltage. Therefore, we have a voltage induced which is having a positive potential at this terminal with reference to this. So, now you can see that the anode of the diode is at positive potential, whereas cathode of the diode is at the negative potential. Therefore, semiconductor diode is said to be forward bias. So, when the semiconductor diode is forward bias, it almost acts like a closed switch. So, therefore, the current flows from this terminal, right, through the diode, then load, and then back to this here. So, therefore, the load terminals are connected to the source terminals and output follows the input here. Whereas, during the during negative half cycle, so the terminal, the potential of this terminal will be at negative potential, and whereas the potential of this will be at positive. So accordingly, it induces a step down voltage of having minus plus potential here. So therefore now what happens, the anode of the semiconductor diode is at negative potential, whereas cathode is at the positive potential here. So therefore the diode is said to be reverse bias. So when the diode is reverse bias, it acts as an open circuit. Therefore the load terminals are disconnected by the source terminals here. So therefore output becomes 0. That is what you can see in the waveform here. So therefore using a single phase half wave rectifier, we can able to get a pulsating DC output, which is shown in the figure. Now let us see also we discussed about the single phase half wave single phase full wave rectifier using center tap configuration. As I told you that there are two types of full wave rectifier. One is using the center tap configuration, other one is using the bridge configuration. So in this full wave center tap rectifier, it consists of the two diodes, unlike the half wave rectifier here. So in this case, you can see friend, the mainly so here you can see that mainly it consists of a diode D1 and diode D1 and a diode D2 here. During positive half cycle, if you just have a glance of this working of this particular full wave center tap rectifier, during positive half cycle of this primary voltage will be at positive with reference to this terminal here. Therefore correspondingly two secondary voltages are induced, that is one is called as Vs1, that is Vs1 here, that is having positive potential with reference to the center tap. Similarly, one more secondary voltage is induced, that is called as Vs2, which will be having the negative potential with reference to the center tap here. Therefore diode D1, it is forward bias, because anode of the diode is connected to the positive terminal with reference to this terminal. Therefore the diode D1 is said to be forward bias, whereas diode D2, its anode will be at negative potential with reference to the cathode here. Therefore this diode D2 is reverse bias. Therefore what happens, the diode D1 acts like a closed switch, whereas diode D2 behaves like an open switch here. Therefore when this diode D1 conducts, a current flows from this positive terminal through the load, through the diode, then through the load and back to this. So this is the flow of the current here when diode D1 conducts. Therefore when diode D1 conducts, what happens, the load terminals are connected to the source terminals, and once again the output becomes equal to the input here. Similarly during negative half cycle, you can see, so the potential of the primary voltage will be having the potential as shown in the figure. So correspondingly once again the two secondary voltages are induced, one is Vs1, another is Vs2. So this particular Vs1 will be having a potential of minus and plus at this particular terminals. Similarly Vs2 will be having the potential of minus and plus. So therefore the diode D1, that is the upper diode, so it is said to be reverse bias, because anode of this will be at negative potential with reference to the cathode here. So therefore the diode D1 acts as an open switch, whereas diode D2 is said to be forward bias, because the anode of the diode is at positive potential with reference to the cathode here, and therefore this diode acts like the closed switch. So therefore, the current how it flows now, when diode D2 conducts, it flows from this terminal through the diode and through the load and back to this. So this is the flow of the current that which flows through the rectifier circuit when this particular it is reverse bias. So therefore, once again what happens, the output follows the input here. So whatever secondary voltage Vs2 is there, that will appear across the mainly the output the load voltage. So therefore, the voltage across the load, what we get is a pulsating DC, but it is unlike the half wave rectifier. This full wave rectifier, it is able to conduct in both the half cycle of the input signal. So now friends, also we have seen also the comparison of the half wave rectifier and full wave rectifier, and also we compared few important parameters. One is ripple factor, another is conversion efficiency and PIV rating. So in case of the half wave rectifier, the ripple factor is more compared to the full wave rectifier, right. So whereas in the full wave rectifier that is using center tap configuration is having a ripple factor of 0.48, that is as the ripple factor. Ripple factor, it is a measure of the AC ripple content of the DC output here. So since in since the half wave rectifier, it conducts only in one half cycle, the ripple content of the DC output is more. So that is represented in terms of, that is 1.21. Usually the ripple factor is defined as the ratio of AC voltage, that is RMS value of the AC voltage to the DC voltage here. So in this case, the ripple factor of half wave rectifier is more compared to the full wave rectifier. And the conversion efficiency, that is the efficiency of the rectifier to convert AC voltage into the DC voltage. In case of the half wave rectifier, the conversion efficiency, the theoretical value of conversion efficiency is 40%, which is much lesser than the full wave rectifier, which is approximately 81%. So therefore, it is mainly because the half wave rectifier, it conducts only in one half. So therefore, naturally the conversion efficiency will be approximately 40%, but however in practice it will be lesser than the 40%. Another the parameter which we compared as far as the half wave rectifier and full wave rectifier is the VM, that is PIV rating. PIV rating is it is nothing but the peak inverse voltage rating. It plays an important role in the selection of the rectifier. Right. So PIV means it is negative maximum voltage that can be applied across the diode without damaging it. So in case of the half wave rectifier, it is equal to VM. VM is nothing but the peak value of the that is the input supply voltage, whereas in a full wave rectifier it is equal to 2 VM. So therefore, what you can say that PIV rating of the diode that is used in the half wave rectifier is lesser compared to that of the diodes used in the full wave rectifier. So this is the one major limitation of the full wave rectifier. Friends, in this particular session, we shall try to understand the operation of the full wave bridge rectifier, and also we will try to know the advantages and disadvantages of the full wave bridge rectifier. And apart from this, let us see the operation of the capacitor filter. Right. So as I told you that the rectifier, they have been classified into mainly two types. One is called as the half wave rectifier, another is full wave rectifier. Full wave rectifier is in turn, it is classified into two types, that depends upon whether it uses the center tap configuration or bridge configuration. So therefore, we have full wave center tap rectifier, then other is full wave bridge rectifier. Already we have discussed about the full wave center tap rectifier. Let us see, right. So what is how the full wave bridge rectifier operates, right, and also let us try to know the advantages and disadvantages of full wave bridge rectifier compared to both the full wave rectifier using center tap configuration and the half wave rectifier. And apart from this, also let us see a capacitor filter. operation, how it operates, right, and all that. This particular slide shows mainly the circuit of the full wave bridge rectifier. Now let us analyze this particular full wave bridge rectifier using, let us draw this circuit here, that is single phase full wave bridge rectifier. So it consists of, as shown in the figure, it consists of a transformer. It is usually called as the step down transformer. Okay, this is nothing but a primary, and to this we feed a single phase 230 volts 50 hertz AC supply, that is very much available. So then we have got an iron core over here. So then we have a secondary here, and please note that this is a secondary voltage. The N1, it represents the number of turns on the primary, and N2, it represents the number of turns on the secondary here, and always for a step down transformer N2 will be less than N1, that is N1 number of turns on the secondary will be less than the primary. So if you have a look at this, friends, we have got, it makes use of 4 diodes, that is D1, then we call it as another diode here, this is the third one, and finally we have got the 4th diode. So this is what we are having, 4 diodes in a bridge configuration. Okay, and mainly here it is, in this case we are connecting a load across the, this is, I call it as RL, and this is D4, I can call the diode D4, this is D1, and this is a diode D2 and diode D3. Okay, now let us analyze the operation of the, okay, this particular bridge full wave bridge rectifier. So as I told you that it consists of a step down transformer having a primary and secondary, wherein the number of turns N2 is less than the number of turns on the primary here. So, and apart from this step down transformer, it also consists of 4 diodes, unlike the full wave rectifier, right, using center tap configuration, which consists of, which makes use of only 2 diodes, and so apart from that we have got a load resistance. Now during positive half cycle, what happens, this, the potential of this terminal will be at positive with reference to this, therefore it induces, this primary voltage induces, okay, a secondary voltage having potential, right, this is called as, I can call it as Vs here. So this is plus and this will be minus. So now what happens here, now you can see that the diode D1, okay, anode of diode D1, it is at positive potential with reference to the cathode here, whereas the even this diode D2, it is at anode of diode D2, okay, it will be, okay, therefore during positive cycle what happens, this particular diode D2 and D1 said to be forward bias and therefore conduct, whereas the diode D4 and D3, right, they are reverse bias, they act as a open circuit. So therefore how the current flows, it flows from the positive terminal of the battery through diode D1 here and through the load resistance, okay, and through the diode D2 back to this. So this is how the current flows during the first half cycle, that is the positive half cycle of the input signal. So wherein during positive cycle the primary voltage will be having the plus and minus potential at this particular terminals. Similarly, this primary voltage induces a secondary voltage which is having a positive potential at this terminal, let us say A, with reference to B here. So now therefore what happens, the diode D1 and D2 will be forward biased, because anode of diode D1 will be at positive potential with reference to its cathode. Similarly, cathode of diode D2 will be at negative potential with reference to its anode. Therefore, diode D1 and D2 are forward bias, whereas diode D3 and D4 will be reverse bias here. So therefore, this diode D1 and D2 are, when they are forward bias, they act like a closed switch, and when these diode D3 and D4, they act, when they are reverse bias, they act like an open circuit here. So therefore, the current which that flows from this terminal A, that is through diode D1 through RL and through diode D2 and back to this. This is the closed path of the current that flows during the positive half cycle of the input signal. So now what happens when diode D1 and D2 are connected, conduct. So therefore, the load terminal, it is connected to the source terminal. So therefore, output, it follows the input here. Therefore, what happens here, mainly if I consider a sinusoidal signal, this is, I will consider it as minus, this is the source voltage, or you can call it as the, okay, that is applied across the transformer. So during positive cycle, so diode D1 and D2 will conduct. So therefore, when the diode D1 and D2 conduct, and whereas diode D3 and D4, right, they will be reverse bias, they do not conduct, and therefore load terminals connected to, will be connected to the source terminals through conducting diode D1 and D2. Therefore output follows the input. So therefore output, it follows the input here. Okay. So now what happens at this, after this zero crossing instant, the input reverses here. So when the input reverses, now let us see what happens here. So now when the input reverses, that is during negative half cycle of the input signal, so this, the potential of this terminal will be at positive with reference to this, and this primary voltage, it will induces, okay, a step down secondary voltage, right, across the secondary winding. Therefore now the terminal A will be having minus potential with reference to the terminal B here. So now what happens here? Now as we have seen, okay, mainly the two diodes, 4 diodes here. Okay, this is diode D1 and diode D2, this is 3 and 4. Now let us see, right, let us analyze this circuit, how the mainly this full wave bridge circuit, bridge rectifier acts here. So now therefore terminal A is at negative potential with reference to B, so the B will be at positive potential, whereas A will be at negative potential. Therefore what happens here? So diode D4 here, anode of this diode D4 will be, okay, sorry, this is other way. Now diode D4, the cathode of the diode D4 will be at negative potential with reference to its anode. Similarly, diode D3, okay, anode of the diode D3 will be at positive potential with reference to its cathode. Therefore, both these diodes conduct, that is D3 and D4, whereas D2 and D1, they will be reverse bias. So therefore, I can represent diode D1 and diode D2 as open circuit, whereas diode D3 and D4, I can consider it as the closed circuit here. That is, it acts as a closed switch. So this is the what we are getting here. This is the equivalent circuit of the bridge rectifier during negative half cycle of the input signal, wherein this potential of this will be having minus with reference to this. Similarly, it induces a secondary voltage of minus and plus. Therefore, the terminal A will be having negative potential with reference to this B terminal. Therefore, accordingly what happens, anode of D1, right, so will be at negative potential, therefore it is reverse bias. Similarly, cathode of D2, okay, so will be at positive potential, this will be reverse bias, whereas diode D4, since the anode or the cathode of diode D4 will be at negative potential with reference to its anode, therefore D4 conducts. Similarly, the diode D3, that is anode of diode D3, will be at positive potential with reference to its cathode, therefore D3 and D4 conducts. So whereas D1 and D2 do not conduct. So accordingly, I am representing D1 and D2 as the open switch, whereas D3 and D4 as the closed switch. Now how the current flows? It flows from this terminal A, okay, then through D4, then so this is through the load resistance, okay, and then through diode D3 and back to this. So this is how the load current flows whenever, that is during the negative half cycle of the input signal, that is when diode D3 and D4 conducts. So now what happens, once again the load terminals are connected to the source terminal through which diodes, that is D3 and D4 here, whereas here the first half cycle the diode D1 and D2 conduct here. So when D3 and D4 conducts, once again load terminals are connected to the source terminals, so output follows the input here. So therefore what is the output you are getting here? It is once again the same as the input here. So therefore, unlike the half wave rectifier, this full wave bridge rectifier, it conducts in both the half cycle, that is during the positive half cycle diode D1 and D2 conducts, right. So therefore once again the load terminals are connected to the source terminals, so output follows the input here. Similarly, diode, okay, during negative half cycle of the input signal diode D3 and D4 conducts, and therefore once again output follows the input here. So therefore we will get that is, okay, pulsating DC, that is right. So this is called as pulsating DC output, that is what we are getting at the output of the full wave bridge rectifier. So this is what, right. So friends, you please note that this particular full wave bridge rectifier, it uses a single winding as a secondary, like compared to, we are just comparing with reference to the full wave rectifier using center tap configuration. Unlike the center tap configuration, which makes use of the two windings there in the secondary here, this full wave bridge rectifier, it uses only the single winding, okay, in the secondary here. And however, once again, unlike the center tap configuration, this bridge configuration makes use of 4 diodes, that is 4 diodes, but however the 2 diodes will conduct together at any one time here. So whereas the full wave the center tap configuration, it is having 2 diodes here, whereas this particular bridge rectifier, it is having 4 diodes. And also you can note that the parallel side diodes conduct at the same time. So as I told you, parallel side means here in this case it was the diode D1 and D2, they conduct together because there are parallel side diodes. Similarly, during negative half cycle of the input signal, the diode D3 and D4 will conduct together. So output waveform will be same as the full wave rectifier, that is using the center tap configuration. Therefore here in this particular slide, we are just having a comparison between the the bridge configuration and the center tap configuration. The bridge configuration uses single winding in the secondary, and compared to the center tap configuration, and bridge configuration also uses 4 diodes, okay, whereas center tap configuration uses only 2 diodes here. And so the output waveform, it is same as that of the full wave rectifier using center tap configuration. So this is what we are getting here. So this is the, okay, positive half cycle of the input supply, AC supply. So what is happening here? So okay, a secondary voltage induces, and therefore diode D1 and D2 conducts here, whereas diode D3 and D4, right, they are reverse bias, acts like open switch, and therefore once again load terminals are connected to the source terminal through the conducting diode D1 and D2, therefore output follows the input here. So this is whatever direction it shows, this direction, right, how the current flows, it flows from this A terminal through diode D, then through resistance R, and through then diode D2 here and back to this secondary here. So this particular slide shows you the conduction of the diodes when the input is reverse bias, that is the during negative half cycle of the input here. So once again here at this point, the terminal A is having a negative potential here with reference to the B terminal, and therefore what happens, so accordingly the D3 and D4 will be forward bias, whereas D1 and D2 will be reverse bias, and so therefore the once again the load terminals are connected to source terminal through the conducting diodes D3 and D4, and therefore output once again follows the inputs here. So that's what we are getting here. Advantages of bridge rectifier: it uses a simple transformer, like unlike the center tap transformer, because it does not require any center tap transformer. So that is there is no question of any extra having an extra winding there. And also the PIV rating of the diodes in bridge rectifier is Vm. So that you need to note here. So how it is Vm, because that we shall analyze it here now, right now. Okay. So in this case PIV means, as I told you, that it is peak inverse voltage rating. It is defined as negative maximum voltage that can be applied across the diode, right, when it is reverse bias. All right. So therefore, so in case of center tap configuration, it is equal to the 2 Vm PIV rating. However, in case of the bridge configuration, the PIV rating of the diode is Vm here. So accordingly, what happens? The advantage, when the PIV rating decreases, then the size, bulkiness of the diode that is used in the rectifier will also reduces, and also the cost of the diode that is used in bridge rectifier, that is also reduces here. Now let us see on the board how the PIV rating of the diodes, okay, in a bridge rectifier, okay, it is Vm. So as I told you, in case of center tap configuration, the PIV rating of diode is 2 Vm, whereas here it is 2 Vm. Now let us assume that, okay, so during negative half cycle, what is happening? This terminal will be having minus negative potential with reference to this. So accordingly, so terminal A will be having negative potential with reference to terminal B here. So therefore what happens? The diode D3 and D4, they conduct together, okay. So then whereas diode D1 and D2, right, they will be reverse bias. Now what is happening here? Now we need to find out, okay, the voltage across this, that is Vd, that is diode D2, and similarly this is diode voltage across the diode D1 here. Okay. In this case, as you know that the voltage across this diode D1, okay, so that if you apply KVL to this, okay, so then you will come to know that the PIV rating of this, the diode, it is just Vm, unlike the center tap configuration here, whereas in center tap configuration it is equal to, okay, it is equal to 2 Vm here, because so that is the advantage here. Even though this bridge rectifier uses 4 diodes here, so since the PIV rating of the diodes used, it is Vm only, the cost as well as the bulkiness of the diodes reduces here, and therefore so accordingly, right, so this is most being preferred compared to the center tap configuration here. So disadvantage also it has got, it requires 4 diodes. So at any instant of time the 2 diodes will conduct. So right, during positive half cycle you have seen, right, the diode D1 and D2 conducts, whereas during negative half cycle diode D3 and D4 conduct here. So at any instant of time, right, simultaneously 2 diodes will conduct, and when 2 diodes conducts, right, there will be voltage drop across the diode, and that amounts to be 1.4 volts if silicon diodes are preferred here. So this particular voltage drop of 1.4 volts, it will become very significant if low DC voltage is required here. So that's why, right. So in that case we are going for a precision rectifier whenever we want to convert a low AC voltage, So in that case we do not prefer such the bridge rectifier in that case. Now friends, let us see, right, some the concepts of or basics of the filter circuit here. As I told you that, right, the ripple means it is a variation in impure DC voltage, right. We have always we need to remember the ripple factor. It is a measure of the AC, that is ripple content of what, the DC output voltage here. So in, as you have seen that, okay, in case of the half wave rectifier it is more, ripple content is more, whereas in full wave, both full wave rectifier using, that is using bridge configuration and center tap configuration, it is very less, because these two rectifiers they conduct during both the half cycle of the input signal. And also due to ripple, what happens, the quality of the DC voltage is reduced here, okay. So that therefore the ripple factor, right, so it is defined as the ratio of the RMS value of the AC voltage to the DC voltage. And also you can note that the ripple factor, right, it is very much independent of the RL volt. That means even whenever there is a variation in the RL, that will not have much effect on the ripple factor, right. So this is what you are saying. And also filter means there are two types of filter circuits are there. One is the inductor, other could be the capacitor here, right. And the inductor also can also store the electricity in the form of PD across it for a short time. And the inductor, as you know, that the current lags the voltage by 90 degree, and this inductor, it allows only the DC current and produces high opposition to the AC current, because we have seen, right, what is the XL equal to, it is defined as 2 pi FL. So therefore the inductive reactance, it is right directly proportional to the frequency, because in this case this is 2 pi and L are constant here, therefore XL is directly proportional to the frequency here. So therefore for AC voltage, the frequency compared to DC voltage, the frequency is more here, and corresponding to the its reactance, right, that is opposition to the, okay, AC content will be more here. So therefore the inductor, it allows only the steady current but opposes the charging current here. Apart from this inductor, a capacitor also could be used, right, to as a filter here, that is to mainly to remove the ripple content of the DC output voltage. The capacitor, right, it also can store electricity in the form of potential difference across it for a short time. Unlike inductor, the capacitor current leads the voltage by 90 degree, and therefore capacitor allows AC current but produces high opposition to DC here. So that means, as you know friends, XC, that is capacitive reactance of the capacitor, it is equal to 1 by 2 pi of C here. From this we can note that XC is inversely proportional to the frequency here, right. So now AC voltage, right, is having, okay, more frequency, higher frequency compared to the DC. DC, as you know, that the frequency of this, it will be the 0, whereas, okay, naturally the frequency, right, of the AC signal is more. Correspondingly, what happens, the opposition, right, to the AC by the capacitor is more here, right, compared to your. Therefore we can say that the capacitor allows the charging current but opposes the steady current here. Now let us see some right, the one capacitor filter circuit here. It consists of a rectifier, okay, and at the output of this rectifier we have a capacitor, and in parallel with the capacitor we have an load resistance here. So this is the output voltage here. So therefore find what we will get, the output at this. Now let us draw this and let us analyze, then we can able to, right, come to know about what is, okay, happening, how this particular filter operates. Now let us see this. You can take any of this one. Now we have considered any of the circuit, maybe you can consider only the half wave rectifier or full wave. Here let us assume the full wave rectifier only. having two diodes. And this is called as diode D1 and diode D2. This is resistance RL, and this is nothing but V naught output. Okay, usually, okay, you can take it outside this resistance. What you can do, it should be connected here. This is your RL. Across this, we will connect a capacitor filter, and this will provide output voltage V naught here. Now, this is whatever you are observing here. So, this is okay D1, and this will be D2 here. This is the input signal. During positive cycle, what happens? The diode D1 conducts. Okay, the load terminals are connected to the source terminal through conducting diode D1. Whereas during positive cycle, this is diode D1 is forward bias, D2 is reverse bias. So what happens? Okay, current it start flowing from A terminal through diode, right? So then through the resistance here, right? Current flows here. That is one current. Other current path will be, it also flow through the capacitor here. So therefore, capacitor, what happens? It gets charges towards what? The input voltage here. So therefore, if you look at this waveform here, so therefore during positive cycle, the filter output will be at this point. Okay. So once again, what happens during negative cycle? Negative cycle, this will be okay minus potential, this will be plus. Therefore, accordingly, the second voltage will be having minus and plus, and accordingly what happens? The diode D1 acts as an open circuit. Okay, so this diode D1 it acts as an open circuit, whereas diode D2 it acts as a closed switch here. So how the current flows now? It flows from the terminal B, that is okay through resistance. This is the one path of the current here. Other could be, so this is one part. Okay, this is the other. So once again what happens? The capacitor will start charging to the input voltage here. So it will start charging here. Okay, it reaches the maximum value during negative cycle, and then what happens? Finally, it will discharges till the input voltage it reverses here. When it reverses, accordingly you will get okay. Once again, the capacitor will start charging, and it will reach the peak value whenever the this output voltage reaches peak value, and after this peak here, the capacitor will start decaying here, because this capacitor during this instant, this is whatever we are saying now, this is called as the charging time, whereas this time what I have indicated, this is called as the discharging time or the capacitor decaying time here. So that is what's the output we get here across the output of the filter. So therefore, finally the expected output is what here? Expected output is actually the continuous DC, but what we are getting here, it is, this is a pulsating DC here. So that is pulsating DC means the DC having an AC content here. So right, so that is what we are getting across the RL. So when filter circuit is used, load must be connected across the output. When during the positive cycle, the capacitor charges to Vp, and it maintains that constant voltage here. So and also please note that usually the value of RL, it is always large here, that is to mainly to maintain the voltage across the capacitor at a constant value. So therefore, if the RL, assumed value of RL is large, and then so the capacitor will be able to maintain its a constant voltage here. Concluding this, so now we have seen three type of rectifier. One is half wave controlled rectifier, another is a full wave controlled rectifier using center tap configuration, then full wave rectifier using bridge configuration. So these three parameters we are looking at mainly important. So, one is ripple factor, another is conversion efficiency, the third one is the PIV rating. As I told you, ripple factor is what? It is a measure of AC content of the DC output here. In this case, okay, in which case it is more? It is a half wave rectifier, it is more, because half wave rectifier it conducts only in during positive half cycle. So, therefore, naturally the ripple content of the present in the DC output is more here, and therefore, consequently the ripple factor is more. So, that is 1.21 compared to the full wave rectifier, full wave center tap rectifier and full wave bridge rectifier. In this case, it is only 0.48. And our second parameter what we are comparing is the conversion efficiency, that is the ability of rectifier to convert AC into DC here. Okay. So, therefore, what is the output here? DC, input is AC, therefore, efficiency it is usually defined as the ratio of output by input here. So, that is it is a ratio of DC output divided by the AC input here. So, in this case in half wave rectifier definitely the conversion efficiency is less. Okay. So, but in both the full wave rectifier using center tap and bridge configuration it is 81.2% here. And last one is PIV rating. PIV rating, as I defined you, it is the maximum, that is the negative maximum value that can be applied across the diode without damaging it here. So, here only in case of the full wave rectifier, the PIV rating of the diode used in that it is 2 Vm, whereas in half wave rectifier it is Vm, and PIV rating of diodes of the bridge rectifier it is Vm here. So, conclusion, what is the conclusion? Even though the full wave bridge rectifier uses 4 diodes, it provides less, okay, ripple factor, that is 0.48, and then more conversion efficiency, that is 81.2%, and it uses diodes having a PIV rating of just Vm here. So, what is the advantage of having less this one? The PIV rating, the bulkiness, that is size of the diodes used in the rectifier also reduces, and also the cost of the diodes used in the bridge rectifier reduces. Therefore, the conclusion is that, so compared to other half wave control rectifier and full wave center tap rectifier, the full wave bridge rectifier provides less ripple factor and more conversion efficiency and less PIV rating. It is being preferred compared to the other two types of rectifiers.